Yes, I'll be discussing navigation of animals and robots, and following up on the instructions given by the organizer, which I think it's awesome to be here. I'll give a broad overview of what we've been doing on navigation in the past few years, stressing, of course, what's been done without much details. Feel free to ask during the questions, and stressing what's not been understood and what's the future. And I'll restrict to macroscopic animals and navigation mostly. I won't mention bacteria, almost not mention bacteria. There's just be a parenthesis. And I'll give 3 examples, one on olfactory searches, soaring flight, and trail tracking. So let me get started with the phenomenology, which is, speaks by itself, and start with the olfactory searches. So what's the phenomenon? The phenomenon is that you have female moths. That's the source of pheromones up here. They are emitting pheromones at a rate which is very minute. We are talking about picograms per seconds. And the Daltons don't bother with the specific number. This number, this Dalton thing, is just to tell you that these pheromones don't sink. They fly up in the air. They get transported by the wind. And they can get to distances which are tens or even hundreds of meters. And then the almost miraculous thing. Yes. Yeah. That's better? Maybe like this? That's probably better, yeah. Yeah, okay, good. And then what the thing which happens is that the male moths pick on this very minute amounts, which come in very sporadic manner. And in timescales of the order of minutes, they are able, following these tracks, which are not real tracks because they are broken, as you will see later. They happen sporadically. They are able to make it over tens of meters in a few minutes up to the source. And of course, I don't need to tell you that this is very important from the point of view of evolution, because this is about mating and reproduction. And how this is getting done, how they manage to navigate into this environment, which is quite different from the environment we are familiar with in bacteria of chemotaxis, it's unknown. And that's what the problem is. Now, still staying in olfaction, but now sticking to the ground, there's olfactory trail tracking. Now, the phenomenon is the same. You're following up a trace of some odors, but the statistics is quite different and the conditions are quite different. In particular, the trail now is getting laid on the ground, and it's a real trail. So you have a trace on the ground that the animals are following up. And there's quite a number of animals that are able to realize this feat. Here you have examples. For example, here you have the ants. We humans are it's being said that we are not particularly good with olfaction, and it is true in the sense that we are not quite as fast as ants and rodents, but we're still able, getting sufficiently trained to move into this trail, to track this trail, as it was shown in this paper here. We go centimeters per second, which is not that great, but we're still able to do it. Now, the animals that really do this in quite an astonishing manner are the rodents. And the experiment which was done by Balla and collaborators here is to put the animals onto a treadmill. This treadmill, you can lay down the traces, just drawing here, and then the animal, they follow the trail. What you see here is that as long as the trail is smooth and regular, the animals are very able to stay on track. They barely get out of the trail. It's something which is probably too easy for them. The interesting behavior happens when you start breaking the path or making it very curved. And then you see something which is quite impressive, and I think it speaks of what the animal is really doing, which is that you see a behavior which is reminiscent of what you've seen before in the kind of insects. There was this behavior that I haven't quite mentioned before, but maybe I should stress now, which is that the way the insects get to the source is by alternating between these two phases. A phase where they consistently move upwind. The arrows are the local direction of wind. And then you have these phases here that are cutting across the wind, which are called casting. And the control of these two phases is the main problem. How do they control these two phases, and how do they get to, as a function of the receptions that they have? This casting is also something that you see here. And the other thing that you might notice, which will be important later on, is that the amplitude of these oscillations, it's somewhat like the animal was extrapolating the path. I'm anticipating on the theory that I will present later. These oscillations are getting wider and wider until the animal is intercepting back the path. So again, the problem is to figure out how this is getting done by the animals. And as I will tell you momentarily, this is also important for robotics because, of course, you would like to get this done with robots as well. Let me finish this overview of examples and phenomena by the case that Pieter Rein was mentioning this morning, which is the thermal soaring by birds. So what's the phenomenon? Again, the best is to just show you a movie. This is a GPS which has been put on the back of a falcon, which is flying. And it's flying on a plane, and then at a certain point, as you see here, it starts to spiral. So what's happened is that the falcon, at a certain point, it has caught on an ascending current of air, which is typically called thermal because it's coming from the heating of the ground. So in case you can have other sources of lift, you can have, for example, close to a mountain, you can have some lift, which is coming from the orography. In this case, there's no particular orography, so most likely this is coming from the heating of the ground and the fact that the hot air tends to go up. Now, they exploit this hot air not to flap their wings and go up. So this way they have a vantage point and they can act as predator as they like to do. And this phenomenon I was showing for falcons is something which is also very widespread in migratory birds. Migratory birds, it's well known in ecology that they follow routes, and these routes, migratory routes, they follow year after year. And these routes, if you go and check how dense these thermals are, for reasons of orography, of heating and other things, they are pretty dense. They're much denser in thermals and in sources of lift than the standard track. And if you make an estimate of how much they can save by doing by using this ascending current by soaring flight, it's something of the order of 40% of their flight, which means that if they couldn't use this soaring flight, they had to store a quantity of fat which would be almost like half of their body, and therefore they wouldn't be able to fly as well as they do. All these phenomena, just to put some art into this, they've not been observed recently. Leonardo da Vinci, while he was in the Vatican Gardens, he was over there and he was looking over the Palatino. He was drawing this kind of drawing already in the 16th century. And you can see that he's an artist because he's drawing these spirals in a very regular way. These spirals, in reality, are much more complicated, and it will be one point. But clearly, the drawings are quite beautiful. And he picked many things. He picked this soaring. He's picking the gliding that the animals do between one thermal and another one, the repicking of the thing, and the fact that the wind is blowing this way, as you can see, like in this one, this is very realistic. The thermal is tilted by the wind, and therefore the animal has to tilt as well in order to stay within the thermal. Now, I've been talking about animals, but in fact, the other big motivation to get interested in this kind of problems is that humans would like to do similar things with robots. And there's a number of applications that go from the thermal soaring here. There's unmanned aerial vehicles that you can use of course, for drones, military drones, but that's not my favorite applications. There's many other applications that you can have, like, for example, surveillance. Then the big problem is that these autonomous flying vehicles, usually they are limited by the batteries. And having a source of energy like the thermal soaring, where you can turn off the engine and you can just fly by going up and then gliding, it's clearly extending the autonomy by substantial amounts. And that's the source of interest in this kind, understanding how this can get done. Now, this is one application. The other application that you can have on olfactory searches, either on the ground or up in the air, is that people would like to develop olfactory robots that are called sniffers. These sniffers, they can be used, for example, for the detection of chemical leak, drugs, bomb, sea mines, sources of toxic substances. And in addition to the problem of developing receptors for these different odors, there's the problem of how you should be using these traces of odors in order to navigate. And that's where this kind of work comes handy. And that's actually the way I started by now a few years ago, which is to develop strategies of search. And this particular one was based on information theory and how you can, rather than climbing gradients of concentration like in chemotaxis, you could climb gradients of information in order to make the map of where the source might be located as sharp as possible in the fastest possible time. And this allows you to make robots able to search at distances of tens of meters like animals do. Okay, so this is for to give you an overview of this different phenomena. So now let me tell you why a physicist like me, why physics matter into this kind of problems. And there's a number of reasons why it matters. First of all, for example, in soaring, there's the obvious problem that the animal is flying, and therefore physics is involved into the flying. Here, I think I cannot help, because Tom is in the audience and is among the organizers, to say that even less obvious reasons, very non-obvious reasons, in fact, physics can get involved. That's my parenthesis into the microscopic world. Bacteria, apparently, they do a very simple thing, which is to climb gradients and just to go out. In reality, what happens when you start using tools from physics and you really start digging into this problem is that you realize that the conditions are in fact much more complicated, and the environment gets to be quite complex, even though it's just pure diffusion and they're just diffusing, they're just chemotacting away. In particular, this was the work done together with Terry a few years ago. You realize that at the tip of the front of the bacteria that are expanding, there's quite a number of things that are happening with gradients that are getting created, which are sharp, with colonizers, and then the follows up. Therefore, even in cases like this, you realize that getting into with the physics modeling allows you to uncover behind the relatively simple behavior, which is the expansion of the bacteria into a ring, that the environment is quite complex. There's phenotypic differentiation, as has been shown by Thierry and Monet as well. So that's physics matters even at this level in a relatively non-complex, apparently non-complex environment. But let me get back to the, close the parenthesis and go back to olfaction. Here it's really complex because turbulence is involved. The wind which is transporting the odors is typically not a mean wind. It's full of fluctuations. And turbulence, the atmosphere out there is quite turbulent. And as you can see in this plot here, the odors, the traces of odors that the animals perceived are very different from diffusion. They're made up of sharp peaks, like here, that usually come in clustered form. And sometimes they can go up from the threshold of concentration, but most of the time they stay below. There's nothing, there's zero, because the odors are getting mixed up so much that they fall below the threshold of detection and there's nothing there. So now you can appreciate how tough it is for the moths to get to the source, because they have to integrate this kind of signals that come once upon a time, once every, sometimes tenths of seconds. They have to integrate these signals. In the meantime, they have nothing to rely upon. There's no gradient. They cannot quite climb the gradients. And they're still able to get this done in the timescales that you've seen before. Now, the physics question that arises from this is what is the distribution of these signals? What is the distribution of these peaks? What's the distribution of the spacing, the duration of the waves, the spacing between two different waves? And this kind of statistics that of course is very important, because that's the statistics that the animals have to rely upon. And what we did, using the fact that I grew up in doing fluid dynamics, is that you can in fact formulate this problem, and you can use the equation of a scalar like concentration, which is getting transported by a turbulent flow, to make predictions. And in particular, what comes out of this kind of works is that, speaking of multiple scales that were mentioned this morning, the PDF, the distribution of the spacing between the waves and the duration of the waves can actually takes actually a power law form with an exponent which is -3/2. And if this 3/2 is sounding like the exponent of the residence time of diffusion, it's no accident, because that's exactly the reason why this is happening. At the end of the day, you can reformulate everything and show that turbulent diffusion is what matters the most. And therefore, the problem turns into a residence time problem with an appropriate formulation of diffusion. And therefore, the time that these paths stay is distributed like in diffusion with the -3/2 exponent. And then you go and you check on the data, and you can see this kind of behavior well reproduced at distances that are relevant for the searches that you've seen before. And of course, this is important because that's the kind of signals that you want to deliver for the experiments, and in reality, what they have to cope with. Okay, so having said a few things about physics, now let me get to the point as to why machine learning matter for this kind of problems, and in particular reinforcement learning that we've been using. And here I guess we are stepping into not this session, but the next one, which is data-driven and concept model-driven modeling or behavior. Reinforcement learning that we'll be using is mostly entirely data-driven, and then you will see you can mix up data and concept and model-driven in the example that I'll show you later on. And getting back to this session, let me show you what we do with Soaring. In the case of Soaring, there's two problems. First problem is that you want to know what are the control variables that you want to act upon. As in the language of Terry, what do you put on the axis of the control? And in order to do this, we ran some simulation, and we identified two variables that are the most effective one for driving the soaring behavior. And these variables turn out to be the upward acceleration of the animal or the gliders. And the other quantity which is important is the body rotation. So how much, because of the push of the air which is coming, how much more it's pushing on the right wing than the left wing, which is important because if it's pushing more on this side than on this side, most likely the center of the thermal is located here, and therefore you have to curve in this direction and not in this direction here. So these are the two control variables. And then speaking of coarse graining, we started with a very complicated network and so on. And then we realized that we could actually shrink this by a ridiculous amount and get, by the end, to something which is just a lookup table. So what you do is that you just discretize your two variables here, which are the upward acceleration and the body rotation. You discretize them in three values, close to 0, positive or negative, very positive or very negative. So at the end of the day, the values, the control variables that you have are just 9 values here, positive, 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 negative, or positive 0. So all this complexity, all this time scales and so on, it ends up being condensed in just these 9 variables that you have here. And then you have the dynamic variable, which is the bank angle here, which again we discretize in degrees of 5 degrees. This is less surprising that you can discretize. What's surprising is that you can discretize at this stage. And so by the end of all this procedure and all these simulations, the whole behavior gets condensed into a prescription and the lookup table that says, for example, if you observe these values negative, negative, and you're already at a bank angle of minus 10 degrees, go down by 5 degrees and bank this way in this direction. And of course, you can rationalize all this in terms of getting close to the center of the thermal. This is what they make perfect sense in this behavior. If the negative acceleration, if the acceleration is negative, you want to go out as soon as possible, so you tend to go to bank angles that are very large in such a way that you fly out of this badly negative region. So that's what we do, and I think it's an extreme example of coarse graining. And it looked ridiculously simple, so how can you possibly do anything with the lookup table like this? And just to make sure that this was not fooling ourselves with simulation, we did the experiment. So we took a glider, a 2-meter wingspan glider. We went into the desert. At the time I was in San Diego, so it's easy to have the heat on the ground. We went into the desert, and over there you have plenty of thermals. You put a glider, you train the gliders for about a couple of days, and then you let it fly without an engine. You let it fly with this lookup table that I've shown you before, and these 2 variables that I was mentioning. And this is the glider flying at the height of the clouds and staying up in the air for time scales that in good days of sun can go up to 1 hour without the engine up. And the way this is, so this is the glider. This is the kind of trajectory that is seen, and clearly they recall the spirals that you've seen before. This is another example of a spiral. It's going down, and it's starting at 200 meters height, and then it's picking up on the height. And in time scales of a few minutes, it's getting to 600 meters. So that's the behavior. And it's suggesting that, in fact, all this complexity can in fact be coarse-grained into relatively simple variables. Whether or not this is done by the birds, it's an open question. It's tough at the moment to attack the problem on birds because the measurements are relatively scanty. But what's coming out of this is that probably there's some extreme coarse graining. At least it's possible to make an extreme coarse graining and still go up and perform this kind of amazing soaring behavior without having to become an expert in turbulence or having to read books about the modeling of turbulence. So let me get to the example. This was soaring that we've done before the lockdown. During the lockdown, because we couldn't do experiments, we got more into the theory. And I want to present an example of behavior of the trail tracking that I was mentioning at the beginning, because I think it's a good example of many of the questions that arise in behavior. And so I use this example to raise all these questions, which I think are important for the discussion. So what's the problem? The problem is to explain how these animals are doing the trail tracking that I was showing you in the second or the third slide. And the typical model that has been put forward is the following one. It's based, as many models of navigation, chemotaxis. The beauty of chemotaxis is that it's so well understood and seems to be so universal that as soon as you see an animal moving, you think about chemotaxis. So this is no exception. What's the model? The model is that assumes the following, that the animal is cutting the trail, going like this, and therefore the concentration that it feels, it's going to go up because it's approaching the center of the trail. So the concentration is going up, and then as it leaves the trail on this other side, the concentration is going to go down. Therefore, if you have a way of picking up this up and down, then you know that you should be turning and you should go the other way around. So that's the way you can understand this, these oscillations around the trail that were shown before. And of course, this is well possible, and it's a good mechanism. But the problem with this mechanism is that it doesn't explain what I've shown you in the second slide, which is the fact that if you interrupt the trail, the animals are still oscillating. They're still doing these oscillations. And this oscillation seems to be pretty smart in the sense that the amplitude of these oscillations was extending. So it almost looks like the animal is extrapolating the path, and you see where I'm trying to head. The model that we proposed recently, and it completely turns the framework, is not to think in terms of this chemotaxis-based behavior, but to think more in terms of a learning scheme, where what the animals are really doing is that they're using the path detections. So these are detections of the animal. The green ones are when it's detecting the trail, and the red one is where they don't detect the trail. Now, what you can do is that you can use two detections or multiple detections back in the past to extrapolate where the trail should be located. For example, if you detected here, and the most recent one is this one, then you make the line which is connecting the two, and therefore your extrapolation would be that the trail is located this way. And based on the uncertainty and the distance between these two here, you can make a cone of where the uncertainty which is associated with this extrapolation. Therefore, what the problem boils down to be is that you have to explore a sector, an angular sector like this, and therefore it makes immediate sense that when you start doing this, the oscillations are going to increase as a function of the time that you haven't detected, because that's the aperture of the cone that you have. Now, I cannot demonstrate so far. This looks very plausible. It's not proved yet that this is the mechanism, but there's a number of experiments that have been suggested, and they will be tested in the group of Venkimurthy at Harvard. First of all, it explains what I told you here is the surge and casting that you've seen before. Now, one prediction which comes from here, and it's quite non-trivial, is that if the animal is really learning about the path, then what it should be doing is that it shouldn't be giving up. You might imagine that after a certain time that the animal doesn't perceive anything and doesn't intercept the trail, it's going to give up. And indeed, in the experiment, that's what you see. If the animal loses track of the trail, after a while, it just starts doing other things. But the question is, does it start doing other things after a fixed amount of time, or a time that depends on the statistics of the detection that they've seen before? And the prediction that comes from all this is that the animal should be using the detections in order to make an estimate of the correlation length of the path, and therefore give up after a time which is going to depend on the learning and on the detection, the statistics of the detection that has been perceived in the past. One other thing is that one other prediction is that if you start making trails that are interrupted with the characteristic distance between this odor patches that you have, then the aperture of the sector search should depend on the spacing, because the wider is the spacing, the more uncertainty there's going to be. And therefore, you should be seeing that the oscillations, the aperture of these oscillations, the amplitude, should depend on the separation here between these broken trails. Now, I've given you this many more predictions that we laid down in the paper. The point that I want to make is that this behavior hits onto many open questions in the field of animal behavior and robotic behavior as well. One is the recurrent discussion between how much of this behavior is reactive and how much of this behavior is adaptive, which means that the animal is really learning. In behavior, typically, there's multiple scales. The animal, for example, here, what it does is that it starts at the very beginning of a trail. The animal is not doing exactly the same thing as when it's been going on for a while. So the animal clearly has multiple scales of behavior which impact and how the behavior is related to these multiple scales. It's a question which is quite open. The other thing is the extension of memory. The chemotactic model doesn't make the assumption that essentially there's no memory. There's a very short memory of a few seconds. While doing this model here, we are assuming that there's a memory which extends much farther back in time. The question is the internal degrees of freedom. So how this past memory is stored in the brain and how much does it go back in time? How is it stored? It's not obvious in the structure of the memory. So these are many questions that come about in this kind of problems, and it's quite general. It's quite general in the field of behavior, in other situations as well, like a Drosophila, a fly walking, a worm which is foraging. All these questions, they come about. This is just one particular instance of all these different behaviors. And I see I've run out of time, so let me skip this slide, which is about the fact that in addition to multiple scales, you can have multiple modalities of sensing, because usually the behavior is not driven just by one sensing modality. There could be more. And let me just conclude with the sources of funding and the people I had the pleasure of working with. And thank you for your attention. Thanks.